Hi, I'm Quentin Garrido, and I will be presenting the paper Visualizing Hierarchies in Single-Cell RNA Sequencing Data Using a Density Tree-Based Autoencoder. This is joint work with Sebastian Dermich, Alexander Jaeger, Dario Sarletti, Manfred Klassen, Laurent Najman, and Fred Precht. The problem that we are trying to tackle is the visualization of cellular differentiation. So, starting from a data that takes the form of a gene expression matrix, where for various cells we have the expression of various genes, and assuming that this process follows a hierarchy, i.e. in this gene expression space we have a tree from a graph point of view, we would like to visualize this tree in 2D to help analysis. There are two steps to solve this issue. First, we need to identify the underlying hierarchy, and then we need to reproduce it in 2D space. Our method, called DTAE for Density Tree Based Autoencoder, works in the following steps. First, the tree extraction. Starting from a gene expression matrix, we extract a tree by means of vector quantization and using the density of the points to build a tree on it. Then we need to learn a good representation of the data that we'll be able to visualize, using a neural network following an autoencoder architecture, which we'll detail a bit further. That takes as input both our gene expression matrix and the tree that we previously built. We will compute a cost-loss function that we will optimize over several iterations. And then, when this optimization process is complete, we should have learned representations that will both preserve the same properties of the data, thanks to the autoencoder architecture, as well as having emphasized the properties of the tree by means of regularizing the visualization by it. Once this is done, we can directly extract the visualization from the autoencoder by feeding in the original data. Let's take a look at the tree extraction first. First, we need to build a tree based on the data density. There are different ways to build a tree on the data, and a crucial part of dimensionality reduction is to have a prior inherent topology of the data. But a tree built on the point cloud directly would be a bit noisy due to the noise inherent to the data. As such, to avoid this and to regularize it, we first apply vector quantization by means of k-means in order to get some super points, like centroids here, that will represent a neighborhood of points and not like a single point. This will make it more robust to noise. The number of centroids that has to be chosen carefully. If it's low enough, then we won't get a nice presentation of the inherent topology of the data. And if it's too high, we lose all the advantage both computationally and from a noise point of view of using a vector quantization. Once we have this vector quantization here, we have all the vertices on the graph, but we need to build a tree on it. And the simplest way would be to use the Euclidean distances between the centroids, but these have some issues. If we take a look here in the red ellipses, we can see an edge that was built on a low density region of the data. However, there was a higher density region right beside it in the pink ellipses, but here there's no edge, where we would like to have one here. Because even though we have only the coordinates of the centroids, we would like to take into account the data that was used to build it, so the density of the points. To do so, when we will take account the density to build edges and not the length of the edge, which will give us much more robust tree structure that is much more robust to the closeness of the centroids, and that takes into account the density of the points as we would like to. How do we build this tree? So first we compute the k-mean algorithm, use the k-mean algorithm to compute the centroids, which gives us the vertices of the graph. Then the weights of edges in this graph are defined by the density of points along it. How do we define this density? If we take a given point, let's say here, we will look at the two closest centroids, so this one and this one, and we will add 1 to the weight of this edge. We repeat this process for all the points in the dataset, and then we compute the maximum spanning tree on this data to get the densest edges, and this will give us a tree that will follow the data density. Now the question is, how do we reproduce this tree in the lower dimensional space? This is the crucial part of the method, and we will discuss in detail which cost function we are optimizing and how this process happens. So first, we need to use the neural network here following an autoencoder architecture that's composed in two parts. First, an encoder that takes as input original data in dimension n, projects it to dimension d, 2 in our case, and then is projected back to 2-dimension n, thanks to a decoder that's usually symmetric for the encoder. And the goal is that the output of the decoder is the same as the input of the encoder. This would mean that we have done a representation in a low-dimensional space that contains the most salient features of the data and that allows the best reconstruction possible. In the simple case where we have a linear encoder and decoder and we optimize the reconstruction directly, we learn PCA. Okay, but which class function are we using here to both have this reconstruction that is clear and also represent the tree structure in the low-dimensional space? We have 4 paths to our loss function. First, the reconstruction loss that ensures that the representation contains enough information to reconstruct the high-dimensional data. That is the typical loss in a simple autoencoder. And then we have the 3 other losses, push-pull, crispness, and cosine, which are all in regards to the tree. The push-pull loss is the core of the method. It ensures that the density tree built on the representations and high-dimensional data are identical. We will detail a bit further how exactly do we achieve this. Then the crispness loss ensures that the representations are tightly packed around the tree edges. So in order to make the representation more easily analyzable, we would like to follow the tree very crisply, very tightly. And so we would prefer points that are very close to an edge instead of points that are much more spread out around it, which this loss will ensure. And then the cosine loss, which is also purely cosmetic, will straighten the tree to make it more visually appealing. So instead of having twists and kinks in the tree, we would like to have something that's straight to be able to read it more easily. Okay, let's take a look at the push-pull loss, which is the core of the method. I won't detail all the other losses, how they're implemented in practice. Feel free to refer to the paper for more details. It works in 2 parts here. We have the push component and the pull component. Starting from an embedding of a point hi, here the point in blue on the right, we have the 2 closest centroid, ci1 and ci2 in the representation space, here the one in green and red. And we also have like c'I1 and c'I2, which are the 2 true closest centroids, the ones that were the closest in the high-dimensional space. We want to be pushed as far away as possible from the 2 closest ones currently in the representation space and being pulled towards the 2 that were the closest in high-dimensional space. So we pushed away from the current one and pulled toward the close one. It's worth noting that in case they are all the same, nothing happened because the loss is satisfied. We are the closest to the 2 correct centroids. This will reproduce our tree since this is the exact definition of the density that we use. Then the loss is simply the sum of those 2 components over the whole dataset. It's also thing that if we have one centroid in common between the correct ones and the closest ones in the low dimensional space, their loss will both compensate themselves, and we will limit the repulsive force as well as the attractive force. But this is not the exact loss function that we use in practice, as it leads to solutions that are not really appealing visually and that are a bit degenerate. So currently the formulation that I showed right before was not invariant to the length of the edges in the tree, and so it tended to produce representations where we had one very long edge in the tree and all the other points were collapsed, which is not what we want to have. To avoid this, we simply normalize the losses by dividing by the distance between the 2 correct centroids. This gets rid of these issues. Also, not all mistakes are equal. Say that you want to have a point that's closest to the centroid in red here and its neighbor here. If the point is a bit before in the same branch, while this is not the perfect solution, this will not change the high-level understanding of the data. However, if it was closer to this branch here, to the greenish branch here, then it would be a more significant mistake that we want to fix with priority. And to do so, we will look at the 2 closest centroids in representation space. So for a point here, it would be the red one, the correct one, and this centroid here. And we will just weigh the loss by the geodesic distance. We assume that a mistake when you have a high geodesic distance, you should be further apart, which means that we will prioritize these points. This will lead to a better optimization process and help get better representation overall. Now that we have seen how the method works, let's take a look at the dataset that we used to validate our findings. First, we use a synthetic dataset generated with the Fate library that consists of 10,000 points in 100 dimensions. And the inherent topology of the data is that we have 9 branches coming from a common 10th one. Then we also validate our results with a real data set, which comes from the T cell that was studied during an infection on a mouse. This consists of 19,000 points in 5,000 dimensions. The topology that we are expecting to see is multiple bifurcations. Let's take a look at the synthetic data first. So our method, DTAE here, is compared to various other methods, some based on autoencoders like a simple autoencoder with the reconstruction loss alone, so the same method as DTAE but without the tree constraints. DCA, SCVA, and SOCI are also autoencoder-based methods, and we have non-parametric methods such as UMAP, FATE, and Force Atlas 2. We also compare to PCA, which is the simplest method for dimensionality reduction, and any method should perform better than it. As we can see, DTAE makes all the branching events and all the different branches very crisp and very easy to separate, with the backbone branch clearly visible here, and there's virtually no crossing between the different branches, making them easily separable. Most methods don't produce as easily interpretable representation. SOCI also produces nice separation between the branches, but as branches that are not as straight, which can be seen as which is a result of our method implementing the cosine loss. And non-parametric methods tend to also have very much thinner branches. This might make the interpretation more easy, but the issue is that the data has some variance to it. It's not a thin line, it has some variance, which is what we see with PCA. PCA preserves the variance, so it is a good way to show that we actually have some variance that we want to reproduce. And autoencoder-based method will reproduce this variance because they are made to reconstruct the data, and so they need to preserve some of it in order to do this reconstruction. Okay, now we have seen that our DTAE works well on synthetic data. Let's look at real data. So here, we can clearly see that DTAE shows a path of a serial differentiation process that's very easy to analyze. We start from the early cells, then we have the proliferating cells, then we have the exhausted and effector-like cells, and then we have the split to the memory-like and terminally exhausted cells, which are the two end fates that we are supposed to see. Most methods have this path that is clear once you have the label, but the branches are not cleanly separated. Memory-like cells and terminally exhausted cells are not really separated on PCA, on SOCI, and on Force Atlas 2. On FATE, they are also very hard to distinguish. Nonetheless, methods such as UMAP perform extremely well. If we take a look at the tree that we have built, here we have pruned it and only show high density edges to make it easier to look at. We can clearly see that DTAE has the cleanest fit to the tree, and all the points are tightly packed around it. On all methods, the tree is very well embedded. There are no crossing of edges on any given method, on any method here. And methods like PCA and Force Atlas 2 have a nice spread of the tree. However, as we have seen, they have no constraint of tightness around this tree, like we have with the crispness loss, which makes their representation less desirable. All of this highlights the fact that every component in DTAE is very important, both the cosine loss to make branches straight, and the crispness loss to give a representation that's easier to analyze, even though the tree might be well embedded in other methods. Nonetheless, this is only a qualitative evaluation, and we can wonder what happens when we look at more quantitative metrics. We looked at three different families of metrics. Local metrics, like adjusted random index and KNN graph preservation. Global metrics, like Euclidean and geodesic distance preservation using Pearson experiment correlation on pairwise distances between points. And Voronoi metrics that look at how well the Voronoi diagrams are embedded. Overall, no methods perform best on all metrics, and every metric judges a different aspect of the representation quality. For certain metrics, you have parameters like adjusted random index, KNN, and Voronoi-based metrics have a parameter which is the number of clusters in the k-means that's used to compute them. So, to be more fair, we computed for a variety of values of these parameters and then averaged the performance of all of these scenarios. This will remove all the biases to our method. DTAE is biased towards second-order Voronoi diagrams-based metrics, UMAP toward KNN-based metrics, FATE toward geodesic distance preservation, just by the criterion that they are optimizing. So, by using all of these metrics, we are trying to alleviate all the biases that are induced by the optimization process and get a fairer comparison between methods. What we can see is that no method is the best on all metrics, and that on certain metrics, even methods that perform worse visually, like PCA, perform the best for geodesic distance preservation. Nonetheless, when we aggregate all of this in the simplest way possible by computing the arithmetic mean of all of those metrics, DTAE performs the best, slightly edging over SOCI, which performs almost identically, both of the methods performing significantly better than all other methods that we have compared. So I think that PCA is not the worst performing methods with regard to these metrics, but was one of the worst performing ones with respect to visual quality. As such, while this quantitative performance also is a useful tool to analyze a method, it's not the best way to just say the method is better than another, as ultimately for a visualization method, the best judge of quality is people that will be analyzing the data and visualizing it afterwards, and that can say whether or not this visualization is faithful to the data or not. However, this is extremely expensive and not practical in any scenario. So what are the main takeaways of this talk and the limitations of the method? As we have seen, we were able to extract a meaningful tree structure from the data relying on its density. Then we were able to embed this tree in low-dimensional space for visualization by preserving it, which gives us a visualization of the data and highlights this tree, and it was very easy to interpret thanks to the different cosmetic loss terms that we used. The produced visualizations also outperform popular methods, both qualitatively and quantitatively on real and synthetic data, showing that DTAE is a very strong contender when analyzing hierarchical data. However, performance is degraded when the hierarchy assumption is violated, which is not the case for some methods such as FATE or UMAP that can be used on a wider variety of scenarios. Also, currently, we cannot handle multiple hierarchies with DTAE at once, and we need to only use one at a time. This is a limitation that can be easily alleviated, and this which paved the way for future work to further improve this method. Nonetheless, this method performs extremely well, and we hope that you were able to understand the core of the method and see its interest both on real and synthetic data. Thank you.